Section 3.2, the title is Application of Exponential Functions. So this section is really just an extension of Section 3.1, where we were introduced to the natural exponential function in terms of continuous compounding, and we're working with similar formula in this section. Okay, an amount A with no subscript is an amount at a future date, at a future time, t. A naught is a quantity that we start out with, an initial amount, as the workbook reads. And then here's our exponential component e to the kt, and this formula is similar to the continuously compounded interest formula that we saw from the previous section, where the amount of money in an account at a later time is equal to the principal that we initially put into it times e to the rt. Alright, and so instead of P we have A naught, and instead of R for rate we have K. Alright, basically the same function. So we're going to be fitting this to various situations: population, bank savings, charging a battery. So if we scroll down to our first example, okay, the formula is pretty easy to memorize. We have A equals A naught e to the kt, and here K is our rate. So the problem reads, in 2010, town's population is 9,850, and it is growing at a continuous rate, so we can use this exponential form, or exponential description of the growth of this town's population. It gives us a rate, which we'll use in the place of K, 1.8% per year, approximate its population in 2022. So T is going to be the year 2022 minus 2010. So how many years pass in between those two years? What do we get? 12 years. So that's going to be our T. And all there's left to do now is to plug in our initial population, 9,850, the natural exponential function, and K, which we write into our function as a decimal number. Percent converted to a decimal, we move the decimal point to the left 2 places. And now we put in our T, 12. At this point, we just bring up our calculator and we enter 9,850 times e to the 0.018 times 12. Enter, and we get a population of 12,225 if I round it. We don't want 1/8 of a person. Oh, what was that number? 225. And that's all there is to it. Okay, we just take this standard form of the natural exponential continuous growth equation, and we fit it to the particular problem. We have two amounts, one at a later time, one initially, and then we have our growth rate and then our time. So not a whole lot of formulas to memorize in this section. So B, we're going to use it to describe the growth of a certain type of bacteria in a lab. It says it's seen to grow exponentially, 9.5% per day, and so in this case we're going to use T in terms of days. If 10 such bacteria are placed in a lab dish, find the population of the bacteria 5 weeks later. Okay, so we have our percentage, and you want to pay close attention to what amount of time that the rate is based on. So the rate, the 9.5%, is based on days. Okay, so we shouldn't put 5 in the place of T. We want to put 5 in terms of days, 5 weeks. And if we convert that to days, well, there's 7 days in a week. Seven times 5. 35 days. So how much bacteria will we have after 35 days? Let's see. They didn't give us, they gave us the word version of the number 10. That's how much bacteria we had in the dish initially. We convert 9.5% into a decimal, which would be 0.095, and we multiply that by 35. So this is 0.095 per day, and so we multiply by number of days. At this point we need to call in our calculator, and we would take 10 and multiply it by the natural exponential function with 0.095 times 35 as our exponent. Enter. 277.9899. I'll round it to 278. So 278. Okay. This is the population. I guess you could say the number of bacteria, since it said we started with 10 bacteria. Alright. C says graphical solution only. Town's population grows at a rate of 0.95% per year. If the population is 25,000 now, then write a formula for the population P as a function of time T. Alright, so we can take this same standard exponential equation and modify it to fit this particular situation. So for the population as a function of time, so we want to calculate P at a later time, and so that is going to take the place of this A, the amount, because this is the A at a later time. We want to know the population at a later time, so we replace A with P. It said the initial population is 25,000. Alright, that replaces A naught. Then we simply write our natural exponential function, and we fit the KT to the parameters of the problem. We had 0.95%, and if we move the decimal place to the left 2 places, we would have 0.0095, and then we throw in our t. Okay, so this is the function that we were looking for. It's been customized for to fit this town's population growth. Alright, the next question, how many years would it take for the population to double in size as well as to reach 90,000? And C states that we want to do this graphically only. So we'll pull up our calculator, and we're going to have to graph this function. In our calculator, P will be represented by Y and T will be represented by X. No need to change the variables. So we go to the Y editor and we type in the right hand side of our formula, 25,000. The natural exponential E, 0.0095, and we'll use an X instead of a T for time. Enter. And now we look at the graph. Okay. Keep in mind that if we take E and we raise it to 0 times 0.0095 would just be 0. So this exponent would be 0, and E raised to the 0 is 1. And so at time 0, our population logically starts at 25,000. So it shouldn't be a surprise that we don't see anything on our graph. This is probably the scale for Y is way less than 25,000. We can fix that. We know that we're going to be looking for a population greater than 0, a positive one. And again, Y represents our population in the calculator. Y max. What will we use for Y max? Well, the question says that we want to double the population, which doubling the initial population would be 2 times 25,000, 50,000. But then it also asks us about 90,000. So in our calculator, we'll put a Y max of 100,000, a little bit above the 90,000. And then we just sort of take a guess. We only want to look at a certain part of the graph, so we're trying to limit our Y and our X. We want positive times, so we'll start X minimum at 0, and then X max, we'll just sort of have to guess. We'll guess how long is it going to take us to double this population. Let's start out saying 40 years. Alright, we can hit trace, and at 20 years you can see that we have not yet doubled our population. And then even after 40 years we're only up to 36,557 for our population. Okay, the Y is the population, the X represents the time, so we need to go back to our window and put in a much larger time, and it's exponential, so once it starts to increase it'll do it fairly rapidly. I'll just simply say 100 years, and we'll see where that gets us. Okay, we know from the window that the upper limit of our y-axis is 100,000. So how far does this get us? If we hit trace and we arrow over to the right, we get within 210 of doubling our population. And that is approximately 73.4 years. So I'll see how close I can get to y equals 50,000, and I'll enter 73 years. That gets us to within a population of 50,000 we're only 17 away. So I'll just go ahead and call it to double P, then the number of years, and I should use T instead of X. I'm thinking about the calculator. T would equal 73 years. So now to answer the second question, how long will it take to reach a population of 90,000? I'll return to the calculator, and my upper limit for time was 100, and that doesn't quite get us to a population of 90,000. We're only at 65,000. So I'll go back to my window and I will put in 200 years. Graph it again. And you can see that now we've shot up past the upper limit of our y-axis, which represents our population in this case. And the upper limit of our population from our window was y max, and if you check the window of your calculator and if you use the same numbers that I did, we set that at 100,000. So somewhere around in this area we should be able to figure out the time it takes to reach a population of 90,000. So I just simply hit trace and I arrow over until I get close to 90,000. 89,324 is about 700 off from 90,000, and we read the time as 134. So I'll type in 135 years, and now we're within 141 from our population of 90,000. So really couldn't argue with 134 or 135 years in terms of the time. So I'll call it at T equals 135 years, and P equals 90,000 approximately at that time. If we wanted to write an ordered pair for this, we would write 135, since T was represented by X in the calculator. This is T, and then the y-axis was P. So X comes first, or our time, 135, and then 90,000. The second page, and this is the last page of this section, there's only a few examples in this section. We can have things that decrease just as we did for gross. Okay, we call a decrease in population or a decrease in the amount of money, we refer to it as exponential decay. Okay, the formula is similar in that we have an A at some later time, an initial amount A with a subscript of 0, A naught. We still have our natural exponential function E with an exponent of K and T. However, we now have a minus sign in front of our KT. And this causes the amount to start at the initial value A naught and decrease. Okay. This formula to the left, you may have not seen before. We do not have E as our base of the exponent, and what we have is a half. And so this is what we refer to as our half-life formula. So on one hand we have a half as our base, and then on the other, for continuous compounding or continuous decay, we have the natural number e, natural exponential. Alright, and so I think we're going to use both of these. This is typically used to describe the amount of radioactive substance that is that's left after a certain amount of years. Alright, we'll read the remark. In any given problem, we use one of the above formulas only, depending on whether H or K is given. Okay, so K, we're usually given some sort of rate in the form of a percent, and then H is what we refer to as the half-life. In example 2, it says that we have a radioactive substance, an isotope, radium-226. So this radium decays. Okay, it has a half-life. Let's see. Well, they don't give us the half-life formula. They've already given us the formula here. Normally, when we talk about a radioactive substance, we refer to it in terms of a half-life. But here they've already given us the formula that we want to use, and so it's decaying. You can see that the natural exponential function has a minus sign in front of the rate. And so let's see. First thing it wants us to do is find the rate of decay. If we compare this exponential function to the one we were given above, we have a very small rate, and this looks more like this equation here, this formula. So what we have is an initial amount, E, and so we'll compare it to the proper one, and then we have minus, which we have a minus here, which means that the amount that we start out with initially is decaying. And then we have K, which is this number that sits in front of the amount of time that's passed. So the rate of decay in this case would be K equals, as a decimal number, 0.0043. Or we could move the decimal point to the right 2 places and write 0.043%. And this is how much we lose after a certain amount of time. Okay, what is the initial quantity of radium-226? Well, our initial quantity simply sits in front of the exponential function, E. And so, in other words, A naught equals 50. Okay, 50 what? More than likely it's 50 kilograms. The problem doesn't really say. Question 3 says, how much radioactive substance remains after 500 years? In other words, what we want to calculate is A of 500. We want to take this function and replace a t with a 500. I definitely can't do this in my head, so I will pull up the calculator, and we simply type in 50 clear 50 second ln, and make sure you use the minus sign that's associated with the number keys. 0.0004 3 times 500, enter, and we get 40. More than likely, this is 40 kilograms, as I stated over here. Maybe that's 50 kilograms. Doesn't really matter. But we do not have half of what we started with. So in other words, 500 years would not be the half-life. Question B, we're talking about the same, well, no, it says a different particular radioactive substance. So we're no longer talking about radium-226, and we're going to use a different formula, not the AT from above. A particular radioactive substance has a half-life of 20 years. Approximately how much of an initial sample of 50 grams will remain after 15 years? So let's see. If we take some function amount, and it says it has a half-life of 20 years, then what we basically want to do is take the initial sample and multiply it by half. Okay, if we enter in 20, then we want to get 50 times a half, and we want to get 25 from that. Okay, if we put in 40 years, then the half-life has already passed the 20 years. So every 20 years that passes, we take the amount and we multiply it by half. So in other words, in this case, we want to take 50, multiply it by half, which would take us to 20 years, and then multiply it by another half, another 20 years. So 2 times 20 years would be 40. And what we do is essentially multiply the previous result, 25 times a half, and so now we cut that in half one more time and we get 12.5. If we go another 20 years, 20 years more, we would take 12.5 and multiply that by half, and so after the next 20 years we would have 6.25 left. And we can keep going like this, cutting the amount of substance that we have by half every 20 years. That's what the half-life means. 20 years more, 6.25 times 1/2 equals, let's see, 3.125. Okay, and so what happens is that we just multiply by half for every 20 years. So it would sort of make sense, given that explanation, that the formula for the half-life equals the initial amount, which would be the 50, times 1/2 to a certain exponent, and that exponent simply takes the time and divides it up into periods of the half-life, which in this case is 20, but I'll put the general form of the equation here, and I'll put h on the bottom. So for instance, if I once again calculate A of 40, well, how many half-lives is that? It's 2. So in other words, we're going to multiply the initial amount by half twice. So A naught would be 50. We'd have 1/2 with an exponent of 40 over the half-life 20, which would give me 50 times a half. 40 divided by 20 is 2, and this would be 50 times a half for the first 20 years, and then another half for the second 20 years. So in that sense, the formula is definitely logical. All right. It says we haven't quite reached a half-life. We only have t of 15 years, but we just simply replace t with 15. No big deal, and our exponent becomes a decimal number, not a whole. We put in our initial amount of 50. We have 1/2. The t is 15, and we divide that by 20. And 15 over 20 is 0.75. So we won't quite half it because 20 years hasn't passed. We will have a little bit more than 25 left. To figure out exactly how much, have to calculate it with our TI 8450, and I'll use parentheses. Instead of a half, I'll write 0.5. Half and 0.5, same number. Exponent of 0.75. Enter. And we see that we have 29.7 left. Which it did say approximately, so I rounded it, and that answers our question. And that also completes section 3.2.